So we've set up the wave machine and we're going to see, what we can learn from it. So it's really fun to play with. In fact, it's so much fun. Sometimes it's hard to remember that we're here to learn from it. But so I've got it set up and it's nice and quiet. They don't stay that way. But just take any of these and we're just going to lift it up and let it go. Can you see how the motion moved all the way down the machine? And in fact, it even came back because it's still going, right? It's oscillating, it's still moving. Let's try that again. What I want you to pay attention to is what, if you had to show with your hand, what direction is the material or these particles? Which direction are they moving? And which direction is the wave moving? Can you see that the particles are moving up and down? Each of the little clay pieces is just moving up and down, but the movement of the wave is this way, sort of perpendicular, because this is going this way and the wave is going back and forth this way. And when that's true of a wave, we know what kind of wave it is, right? Because there's two different kind of waves. There's this kind and another kind. So think about what that one's called, and we'll come back. Do you think of it? It's a transverse wave, right? Not a longitudinal. Longitudinal is a compression wave, so you can't show that with this machine. This machine only shows transverse waves. You can look at some of the traits of waves, the different things that we measure about waves. One of them is amplitude. That's how big the wave is. So think about how could you figure out or just demonstrate a really low amplitude wave. If I just did a tiny little motion, that's a very low amplitude wave, versus a big motion is a big amplitude wave.
Let's look at two more traits, wavelength and frequency. Can you see if I frequently make waves that the wavelength is pretty short, the distance between each wave is pretty short, that they're small waves, not small in height, but small in length. That's wavelength. And on the other hand, if I make waves less frequently, then the wavelength is longer. There's a reason for that, and those two things I think you can see are connected. You can't really just study one or the other. They're both going to be present all the time.
It's interesting if you set up more than one. We typically have 3 or 4 set up in the classroom so that different groups can work on them simultaneously. I love to have them set up differently. So this one's set up with all clay. Sometimes we'll set one up with no clay. And sometimes, and I'll show you, we set it up with half clay and half no clay. And so there's just interesting things that you can do when you set it up like that. Another thing that's typical, belongs to a wave, would be a trait of a wave, would be the speed of the wave. And that's something, if you would measure it, and you probably could measure it with a stopwatch, that's something that is specific to the medium. So this is the medium, the thing that the wave is made out of or that it's traveling through. If that doesn't change, then the speed doesn't change, because the speed and the medium are connected.
Here we've taken off half the clay, right? So the front of the machine toward us has clay and the back of the machine away from us doesn't. Let's see what happens to the speed of the wave, because the speed is dependent on media, and here we've changed the media. We've changed the machine and the nature of it. So let's try it and see what we see. Can you see that the wave moves more slowly in the part of the machine that has the clay, and as soon as it hits that back part of the machine, the whole back half just twists. It's moving so quickly that it's almost simultaneously in terms of how that moves, because it's moving so much faster. If you've studied motion and you've studied Newton's laws, you might have a sense of inertia, and think about which part of this machine has more inertia. The front half, right? More inertia means it's going to change direction more slowly. And therefore, the wave is going to propagate. In this case, the wave is going to propagate more slowly, which it does in the front half. And in the back half, less inertia, less mass, and the wave's going to move quicker.
So if you're going to set this up in your classroom, it's pretty straightforward. It's just a very long piece of duct tape and skewers and some clay or some kind of weight. I always have kids make these. In fact, these are 6 years old or more, and we use them every year. And they hold up fine. So the first year it took us forever because they all made them. But then now we just pull them out and kind of get them set, adjust them so that they're all working well. Sometimes I put them up with ring stands in my classroom. Just whatever it is, it has to be clamped down pretty hard. You could also tape it to a desk or a table. Sometimes you need to weight. If the desks are lightweight, you'll need to weight those down or they'll flip over, because this has quite a bit of tension on it. So keep that in mind when you're setting them up in your classroom. At the end of the unit, we just wrap them up and pop them in the unit boxes. And then for the next year, when we're ready to go, we just unwind them. The clay can stick together a little bit, but you just pull it apart and then you the kids will figure it out, kind of just trial and error, which is a great way to do it. That the high side will need either more weight, or you can push the weight out further if that's an option. And on vice versa, the heavier side needs to have some weight removed, or you can push the weight toward the center, and that works fine. But I find in general, as long as these are fairly evenly placed and the weights are fairly evenly matched, it should be in pretty good shape, and then you'll just need to do some fine adjustment. I find the kids generally are great at this, so I don't typically do this for them. I think you'll see when you get into this study and using the wave machine that there's a lot going on, right? The wavelength, the frequency, the speed, and you can't shut one down to focus on another one because those three things are connected, so you cannot separate them. But that's what you want to focus on, is how are they connected? So if for a given speed or a given medium, which connects, the speed is determined by the media. So for the given media, i.e. speed, what happens when I increase the frequency? Okay, we did that. What happens when I decrease the frequency? If I need a really long wavelength, what's the frequency going to look like for that given speed? And so if you can get them to start seeing that connection, then you're way ahead. That's what you really want to have them do. I've used the words trait, property, characteristic, behavior. I've kind of used those interchangeably, and I don't think they're super specific in this case. That's not typical for science. Typically, our words are very precise, very specific, and they're not interchangeable. But I just wanted you to be aware that I'm a little mushy there, so don't be surprised. These wave machines, I didn't want to make a brand new pristine one for the video. I wanted you to see that these are the wave machines that the kids made about 6 years ago. This is our 7th year that they're in operation, and they're great. They're fine. We haven't broken. None of them have broken. We get them out always for this unit, but also for some of the younger kids. They study earthquakes, and so it's a great thing to bring out and talk about the different kind of waves that are going through the Earth's core. So that's kind of fun for them.
What about behaviors like reflection and interference? Could you study those with this machine? And the short answer is absolutely, but the long answer is I wouldn't. And the only reason is I wouldn't start there, and I'm not even sure. I'd wait to make sure that the fundamentals are pretty solid before you get into that, because those are subtler concepts and a little bit tougher to study with this machine. I think there are better ways to study reflection and even interference. So those are my 2 cents, but you could definitely do it if you wanted to.